Calculus. Differentiation from first principles. Example 1. Find the derivative of fx equals k from first principles, where k is a constant. Here's a graph of y is equal to fx equals k, where k has a value of 3. So every point along this line, the y value is 3. 0, 3, 1, 3, 2, 3, minus 2, 3, etc. So there are many lines fx equals k parallel to the x-axis. All points are on the red line here of interest. So y is equal to fx equals k. So our point xy satisfies this function. So if we put in the value of x, we find that the y value is on the line y equals k. If we take a different value, x plus delta x, a different value of x, we get f of x plus delta x is y plus delta y. And that too is equal to k. So another point, x plus delta x, y plus delta y, is also on this line. So we can find that even though the x has changed, the y plus delta y, is really the same value, k. Taking one from the other, y plus delta y minus y, is this line here, which is k, minus the first line here, k. K minus k. So we can cancel the terms out now. Y minus y, they'll cancel. K and k, they'll cancel. K and the minus k, leaving delta y is 0. So the change in y value from here to here is no change at all. It's still stuck on 3. So if delta y is 0, delta y divided by delta x is 0. 0 divided by delta x is 0. And at the limit, no matter how small our step is from x to x plus delta x, if it's only this amount or this tiny amount, we'll find that at the limit, delta y over delta x, dy dx is 0. So, we have now, for any constant, y is equal to fx equals k, that if we take the derivative of a constant, whether it's y is 3, y is 7, y is minus 2, dy dx of a constant is 0. The slope of this red line here is 0, and the function does not turn. It never increases nor decreases, it never turns. And it wouldn't matter what values we took, whether we took the values there, original values for x and x plus delta x, or any 2 points along that graph, we would find that the derivative of a constant is going to be 0. We don't always get the opportunity or have the requirement to draw the graph, so we might just do it using the formula. Find the derivative of fx equals k from first principles. So we write the function out, y is equal to fx equals k. The next step is to write y plus delta y, a small change in y, and that leads to a small change in x, fx plus delta x. And in this case, that's also equal to k, because regardless of what value we have in here, we're always going to get k. It doesn't depend on x. Y plus delta y minus y, subtracting the first line from the second, we get k minus k. Cancelling, we get delta y is 0, and dividing it by delta x, we get delta y over delta x is 0 over delta x is 0. And at the limit, when this gets very small and delta y gets very small, at the limit delta y over delta x is called dy dx, and that is equal to 0. Example 2. We now look at a linear function where fx is equal to ax. Find the derivative of fx equals ax. For example, fx is 3x, or what fx is 7x. And we're going to do this from first principles. So y is equal to ax. The next line is to put y plus delta y. And everywhere we had our x, we now plus x plus delta x. So instead of ax, we get a into x plus delta x. And multiplying in, we get y plus delta y is ax plus a delta x. Subtracting the first line from this line here, we get y plus delta y minus y is ax plus a delta x. minus ax. Now we can do some cancellations. The y's cancel and the terms in ax cancel. So delta y is a times delta x. But we want delta y divided by delta x, so we can divide both sides by delta x. So delta y over delta x is a times delta x over delta x. Or if we just took that across, we just find that it's equal to a. So we can see those terms cancel, or we find that delta y over delta x is a. And at the limit, when these are small, delta y over delta x becomes dy dx. And again, that's left equal to a. So if you differentiate y is equal to ax, you're left with just the coefficient that's there before the x value. So here's a graph of y is equal to ax. The point xy and the point x plus delta xy plus delta y slightly moved on from there. Change in the x value of delta x, a change in here of delta y, and we're interested in delta y over delta x, this ratio here, or the slope of this line. So for y is equal to fx equals ax, we found that dy dx was a, so the slope of that line was a. We just used the coefficient of the x. The slope is constant, it never changes, and the function doesn't turn. So this line continues indefinitely at that slope value and never turns, whether we used this point or a different point. So here we are, whether we used xy or this point down here, any point along that line, we would find that it has the same slope and the function does not turn.